Thank you, Sujit. I expect you're expecting some sort of story, after-dinner speech, a joke. I don't have any. I was hearing from Maria Heckel, who said that when she did an experiment once, a Rika tube experiment, she set off with a flame, set off the fire alarm in British Gas, so the entire building had to be evacuated. I thought that was pretty funny. I've never done that myself. But before I start, there are a few things to acknowledge with this. You can't hear me? Is there a way to turn the volume? Is it the noise? Yeah.
You would have to wear another microphone.
Ah.
We can.
That's no problem. Yeah.
Stereo.
Problem is, this one goes over the speaker, and we don't have.
Shall I just speak really loudly?
No, I would turn this on in a minute. Mikro. Jetzt müsste Sorry for the inconvenience.
No, it's fine.
Oh,
Now you can hear that. Wow. Good. Right. Sorry, that was my sort of general PhD supervisor laugh. So people to thank for this presentation. Luca Magri, who's sitting there, halfway through, will come up to Luca's work. Gary Chandler was a PhD student who's now left. Ube Quadri just submitted. Uti Tamasola, some of her work will be coming in later on. You'll notice that, Alessandro, Giulio and Kartik aren't thanked here because they're talking tomorrow and they'll show you what they've been doing tomorrow. Peter Schmidt, from whom many of these ideas came in the first place, he's been very helpful. Colm Coldfield in maths. And then I think finally, there's a lot of the ideas in here come from Flavio Gianetti, Paolo Lucchini, and Jan Pralitz, who at the time were in Salerno in Italy. So I think it's a good idea to sort of acknowledge where they come from. And if you go really far back, a lot of the ideas actually happened by a guy called Derek Hill in 1992, who did these two fantastic papers in the early 90s that then just disappeared from view and then resurfaced again in around 2007. Now, I was working up to the wire on this, so I didn't, the little stick you have, this presentation is not on that little stick. So if you want to find it, you have to hold your nose, type Matthew Juniper into Google. This will come up. And if you look at postgraduate teaching, the N3L talk is sitting on my website now. If you type Matthew Juniper into Google, you'll find 4 Matthew Junipers. One of them is a schoolboy in Scotland. It's not me. One of them is about my age, and he's distinguished for 2 reasons. First of all, he brews his own beer. He lives in Portland, Oregon, in the States. And secondly, he is the Portland, Oregon champion of lawnmower racing. And that's not me. The third of them lives in Australia on an island, and he sails boats, yachts, for a living. Sadly, that is not me. The fourth Matthew Juniper, the one slightly balding, etc., or maybe completely now, up there, that's me. And if you find that postgraduate teaching, there's a number of different courses, control, flow and stability, and this one here on thermoacoustics. Anyway, I'll move on. Let's imagine we have our gas turbine system, the combustion system here, and we might have made an acoustic network model of that. This is actually taken from one of Anne Dowling's papers, where they've made an acoustic network model, so modeling the acoustics in the combustion chamber. With some flame models here and here. This is what the model might look like, and it could have many degrees of freedom. Many really depends on how much detail you put into the combustion. At the simplest level, you might have a few tens of degrees of freedom. If you really make a complicated combustion model a la Surfax, you'll have 10 million, 80 million degrees of freedom, an enormous number. So having got that, you might then work out the linear modes of the model. So I'm talking now about a linear analysis. With this very nice talk from Rama Govindarajan that 1 or 2 of you saw, I think, in May. Coining Tolstoy, she says that, linear systems all resemble each other, but nonlinear systems are nonlinear in their own way. So all linear systems are similar, and that means that you can use analysis from one linear system and apply it to another, which is really strong. Nonlinear systems are all a little bit different. Sujit might disagree, but I thought it was a very nice phrase. What we're going to do now is look just at linear analysis and take ideas from hydrodynamic stability into thermoacoustic stability. So having made a linear model of a system, which would be something like this, we would then look at the eigenvalues of that model. So you'd have frequency on that axis, say, growth rate on that axis, and you'd find only certain oscillations can exist. So at a given frequency, let's say here, there's a growth rate that's negative, so this is stable. But at the frequency here, there is an eigenvalue of the problem which is unstable. It has a positive growth rate. So typically a linear analysis would give something like that. Now can I pause for a moment and little nods if that's fairly familiar, little shakes if it's not so familiar. Kartik's just playing with me. Of course it's familiar to Kartik, but I suppose you've been doing nonlinear stuff. I'll go really slowly just for Kartik. Anyway, so you might get your eigenvalues of the system from a linear analysis. Now let's imagine you want to see what happens when I change one aspect of the system. So let's say I change the main burners. All the eigenvalues will shift. I mean, not just the unstable ones, the stable ones will shift as well. And you could work out how you could make that change to the main burners, recalculate your eigenvalues and see how they've all shifted. That might be a sensible thing to do. Of course, if you wanted to do that for every single change in the system, you would have to do as many calculations as there are degrees of freedom in the system, +1, in order to work out how the eigenvalues shift when you make a small change to each value, to each parameter in the system. I think sort of liken that to standing on a hill. Imagine you're standing on a hill and you want to work out which way is up. You could take a step forward, find out whether that goes up or down, a step to the side, find out whether that goes up and down, and then you find the grad, or the steepest line through those 2 points, and that gives you the line that points straight up the hill. Imagine doing that for a 1,000,000 degree of freedom system. You need to do 1,000,001 different calculations in order to get all those gradients. Now, what if you could do that with 2 calculations per eigenvalue? So you go here and say, I've got 3 eigenvalues that I don't like, they're unstable. What if you could work out how they change due to changing any parameter in the system, any of the degrees of freedom, in just 2 calculations? Wouldn't that be amazing? The future is now, because we can do that. And the way to do it, well, I thought about a number of different ways of explaining how to do the miracle cure. And this is a way that I saw Jan Pralitz use just a few weeks ago, and I really liked it because it starts from something which I think everybody's come across before. And everything is derived from this, the eigenvalue decomposition. So I guess you've all seen that before. Even if you don't remember seeing it before, you've definitely seen it before, you just ignored that part of the course. But let's say you've got a matrix. I'm going to talk in terms of matrices now, but this also applies to operators. So a matrix acts on a discretized system, an operator acts on a continuous system. Otherwise, they're pretty much interchangeable. They are the late people. Sit at the front. Plenty of room at the front. Oh dear. I was just saying, for the benefit of those who've just walked in, this is what we're talking about this evening. It's a miracle cure. Let's say we've got a thermoacoustic network model that has many degrees of freedom. We've got its eigenvalues here. And if we want to work out how the eigenvalues change, when you change each degree of freedom, you can imagine doing a finite difference calculation which would take you as many calculations as there are degrees of freedom. Or we can use the miracle cure, which finds out how each eigenvalue changes under any change at all in the system in just 2 calculations. And this is how we do it. So we're going to start from the eigenvalue decomposition. Sebastian, earlier on, when he saw this slide as we ran through it in practice, looked at this in shock and said, "You're showing equations today." I am indeed showing equations today. Normally I just show pretty pictures, but today we've got some equations because you've all had some alcohol-free beer, I noticed upstairs. Thank you very much, Wolfgang. And so you'll be able to cope with some equations. So we're going to start from the eigenvalue decomposition, just saying we can take any matrix. Like I said, it can apply to operators as well, but it's much easier to explain in terms of matrices. So take any matrix L, can be split up into the matrix in the middle, which contains the eigenvalues along the diagonal here, a matrix Q here, which contains the eigenvectors as column vectors, and then Q inverse here. Now often you'll have seen it like this, and so you might work out Q, which are what are commonly known as just the eigenvectors, and then that's Q inverse on the right-hand side. I'm going to label each of the rows here, Q1 dagger, Q2 dagger, Q3 dagger, and so on, and give those a meaning. And that is actually the sort of the crux of this argument, the important part of the argument. So I guess you've seen this before. Yeah? Right, eigenvalue decomposition. Let's post-multiply by Q. So if we take that post-multiply by Q, so we get LQ equals Q sigma. And now we have a simple, you'll have seen this before, L acting on a vector is equal to that vector times its eigenvalue. And then I think I've got the second one. L acting on the second vector is equal to that vector times the eigenvalue. So we can write each of those columns, if I label them I can write this equation here. For each value of I, L operating on Q, the eigenvector, is equal to the eigenvalue times the eigenvector. So you'll have seen that before, and you'll know those as the eigenvalues. I want to call those the right eigenvalues, by which I mean the right one, the ones on the right-hand side, not the correct ones. That's the right eigenvalues. Now, on the other hand, let's pre-multiply by Q to the minus 1, and now we get Q to the minus 1 operating on L is equal to sigma Q to the minus 1. Now, Q to the minus 1 is a matrix, so it's fine to operate it on a matrix. These are all square matrices, by the way. But I can think of it in terms of this row here acting on this matrix is equal to the eigenvalue times that row there. And I know that that row and that row are the same because this matrix is the same as this one. So it's really just exactly the same thing, but with a different vector here, that instead of being, if I go back 2 slides, a matrix acting on a column vector, it's now a row vector acting on a matrix. And this is perhaps a bit less familiar, but that's known as the left eigenvector. So it's the same sort of concept. It's just we found the inverse and taking the top row, the inverse of Q and taking the top row, instead of taking just the column, like that. So right eigenvector, left eigenvector. And the way I can write this is Q dagger transposed. Hermitian means conjugate transpose, so I take the complex conjugate. That's optional. I could just take the transpose. It's just a little bit neater if you use the complex conjugate. Operating on L is equal to sigma times, this is a column vector Q, the way I've defined it, so the Hermitian, the transpose, just makes it into a row vector. And so that works for the second row and the second eigenvalue. Now, by construction, Q to the minus 1 operating on Q is equal to the identity matrix because Q is the inverse of Q. And this shows you straight away that the top row here, operating on or times the first column is equal to 1. The second row acting on the second column is also equal to 1. But the second row acting on the third column and the fourth column, etc., is equal to 0. So we see that the vectors Qj and Qi are equal to 1 if I is equal to j, and 0 if I is not equal to j. And that's known as the biorthogonality condition. So if I have, this is where we're non-normality. So if the matrix L is normal, its eigenvectors are all orthogonal to each other. So if it's just a rotation matrix, for example, its eigenvectors would be orthogonal. Have I got that right? I think so. The eigenvectors would be orthogonal. And then you'd find that Q to the minus 1 would equal Q transposed already. But if they're non-orthogonal, then that that vector there is not the same as that that vector there. Anyway, this is the sort of way to describe or to introduce all the concepts in terms of the matrix eigenvalue decomposition. And that's really sort of the fundamentals to adjoint stability analysis. I'll build up on it now, but has anybody got any questions at this point? Tim, you look as if you've got a question. No questions, Your Honour? Okay. Anybody else? Right. So, in summary then, if I start from the eigenvalue decomposition, I'll create some things called right eigenvectors, which you'll know as the eigenvectors, and then the left eigenvectors, which are a bit less common or commonly used. If the matrix is normal, then the left and the right eigenvectors are equal to each other. If it's a non-normal matrix, then they're different from each other. Now starts the fun. Let's take a problem in the time domain. So it's a linearized problem. There's my operator or matrix L. Here's my state vector Q. It could just be any old vector, but typically in a CFD calculation, for example, it would be the velocity and the pressure at each point in space, just arranged as a long column vector. And let's say we just get d by dt of Q is equal to L times Q. So I've made my linear operator or linear matrix L, defined it such that the evolution of Q is just L times Q. Obviously, I'm using matrices, so this is a linear framework. Now, if t runs from 0 to infinity, then Q can be expressed as a sum of eigenmodes. And this is just saying that Q, my vector here, is equal to alpha I, just a number for each value of I, times the eigenvector, the ith eigenvector, e to the power of sigma it. So I'll just take that basis set, if you like, and plug that into that equation. I'll get I equations, each of which has to be satisfied, and that's simply that sigma I qi, which comes out of this exponential, is equal to L qi. So basically I get a whole load of equations, each of which obeys this eigenvalue problem. So again, that's, I hope, fairly standard. And each of these eigenvalues is the right eigenvalues of L, the way this is written. So I can rearrange this to be L minus sigma I operating on qi, the eigenvector, is equal to 0. Okay? Right, and just as a reminder, that's just this. See, I've reckoned that you'd have had a couple of beers by now. So it's all going, at the moment, very slowly. I hope that if there's any problem, just a little shake of your head, that's all you need. Don't even need to say who you are. If I know your name, by the way, it's generally very bad news in my lectures. Right, so that's just where we were before. We're looking at each eigenmode separately. Qi is the eigenvector, sigma I is its corresponding eigenvalue. Now let's consider what happens when we make a very small change to the linear operator. So we say L is going to go to L plus epsilon delta L. That should be a bold L. Never mind. When we do that, the eigenvalues and the eigenvectors change a little bit as well. So sigma I will go to sigma I plus epsilon delta sigma I. I've just used the epsilons there to stress that it's a small number. I could have left it with just the deltas because that also implies it's a small number. Qi, the eigenfunction or the eigenvector, goes to Qi plus epsilon delta Qi. So all I'm going to do now is substitute these three changes into this above equation here. And basically this will be satisfied as well for my new eigenvalue problem with the new operator L plus epsilon delta L. Okay, so the next slide will just take the bottom line here and put it to the top. So all I've done here is write down my new eigenvalue problem. At first order, epsilon to the 0 is just the same as the old eigenvalue problem. At order epsilon, it looks like this. At order epsilon squared, it's just got some epsilon squared terms coming in here. I'll ignore those because epsilon is small. So I'm going to first order in epsilon. And I get this expression here. Now, here's the clever bit, although hopefully it'll seem fairly simple. We pre-multiply by the corresponding, so the ith, left eigenvector here. So we pre-multiply. We need the Hermitian because this is a matrix, a square matrix. This is a column vector here. So we make the Hermitian transpose in order to make a row vector acting on a matrix. And now, just a little reminder, the row vector acting on the matrix is just equal to the eigenvalue multiplied by the same eigenfunction. We can rearrange that like that, and we can see that for as long as I, these are the same I, this is always equal to 0. So when I pre-multiply by the left eigenvalue vector, this term here disappears, and all I'm left with is this term. And now I just rearrange it, and I get that the change in the eigenvalue is equal to, wait for it, any change in delta L operated on the eigenvector you're interested in, pre-multiply by the left eigenvector, and then divide through by this thing here, which is equal to 1 if you've constructed your eigenvector as well. So what this is saying is, let's say I've found one of those eigenvalues. I think no. I found one of those eigenvalues. I found the corresponding eigenvector. All I need to do is work out the corresponding, so I found the corresponding right eigenvector. All I need to do is find the corresponding left eigenvector. And then, no matter what my change in delta L is, I can work out what the change in sigma I is in just one more calculation. So it's a really neat way of getting all the gradient information about delta I, about the eigenvalue, without doing any more calculations. All I need to do is work out this, the left eigenvector, which is also known as the adjoint eigenvector. Right. Now I could. So I want to work out these eigenvectors, the adjoint eigenvectors or the left eigenvectors. I could work out all the eigenvectors of the problem, take the matrix, invert it. But that takes quite a long time. On the other hand, if I start off from the problem that I know to be true, that the one I want to start with, I want to find this eigenvector, I'll just take the Hermitian of this problem, so the transpose of this problem. When you take the transpose of two matrices, you swap them and take the transposes individually, so that gives me this problem. A Hermitian can just pop inside the brackets. I Hermitian is equal to I, sigma Hermitian is, because it's the conjugate transpose of the complex conjugate, so I get this expression here. So the left eigenvectors of L are just the right eigenvectors of L Hermitian, so the transpose of L. So that's the easiest way to find the corresponding eigenvalue. So what do? If I had MATLAB and a small matrix, I can work out all the eigenvalues and all the eigenvectors at the same time. Job's done. For many systems that are bigger, you'll use an iterative technique to find the eigenvalues and the eigenvectors. Now, in doing that, you often find just the first 2 or 3. You don't want to find all of them because there are 10 to the 7, huge number. So what I do is I find the eigenvalue I want to find, I find the corresponding eigenvector, and then I just take L Hermitian. I know what the eigenvalue of this problem is already. It's just the complex conjugate of the eigenvalue that I want to look at. And then I don't even have an eigenvalue problem anymore. It's just finding the null space of this matrix here, and that's the left eigenvector, or the adjoint eigenvector. In practice, I find it's just as quick to do an eigenvalue calculation again, but you don't strictly need to. So this is a very quick way to find the corresponding adjoint eigenvector for a direct eigenvector, or in the original language, to find the left eigenvector for a right eigenvector. Right. Any questions? Wolfgang.
If you happen to come across a change in L, which has no change in the eigenvector, could be.
Yeah, there is one.
With delta L with delta Q 0.
Yeah, there's only one though, which is that more of L. If delta L is proportional to L, then the eigenvector won't change, but the eigenvalue will increase by the same proportion that you've increased L.
But even, okay, so this problem isn't really something you're like. My question would have been, does then the procedure blow up? But I don't think so, right?
No.
There's no division by 0 or something. No.
I don't think so. No.
It's only one condition. I think it's more conditions.
So what I was saying to Wolfgang said, are there any conditions for which the eigenvector doesn't change? And there is one. If L just goes to 1.01 times L, then the eigenvector stays the same, but the eigenvalue goes to 1.01 times sigma I. That's certainly one condition. My hunch is it's the only condition, but maybe I'm wrong. Yeah. I find standing up in front of a bunch of people, my IQ drops to even lower. So I won't attempt to work that out now. I think it's right, but I don't swear to it.
I think there's more than one. But
Bruno thinks there's more than one. Upstairs in the cocktail lounge. Yeah. Anyway, never mind. Right. Now, when doing this sort of thing, I always like to go back to something really simple that even I can understand. And in this case, there's a summary. Oh, crikey. I've jumped forward 2 slides. So anyway, this is the process that one has to do. I'm sorry for the I'm trying hard not to lisp, that sort of noise, but it's not working. I can hear it coming over the speakers, the S sound. I apologize for that. So here's what you do. Express your problem in state space form, so time domain form. Choose one of the right eigenmodes, which is the eigenvalue that you want to look at. Find the corresponding left eigenvector by taking L Hermitian and finding its right eigenvalues. And then you use this expression here. The change in sigma from the change in L. Now, delta L could represent a change in the base state. It could be the addition of a passive feedback device. So by that I mean something that you just put in the flow or put in the system. It doesn't do anything, it just sits there. The addition of an active feedback device, so you could have a sensor like a microphone, an actuator somewhere else like a loudspeaker. You can express that in terms of delta L. It could be a change in one of the terms in the governing equations. This is my favorite trick at the moment. Take a set of governing equations, and then you can see how much each term in the governing equations contributes to the eigenvalue. So there are some terms, each of which will have a physical meaning, which make no influence and which have no influence on the eigenvalue, and other terms that have a huge influence on the eigenvalue. So you can start to probe physically to see what is it that's causing this oscillation. And then the way it's been used traditionally is the bottom one, is to find, you can think of it as finding the most influential feedback mechanism at each point in the flow. What that really tells you is which region of the flow is the wavemaker region, which region of the flow is causing the oscillation, whereas much of the flow will just be responding to an oscillation in terms of a flow. And I'll look at these, more or less each of these in turn during this talk. Like I say, I like to go back to something really simple. Here's something you can do by hand. Let's take a simple linear oscillator, x double dot plus bx plus c equals 0. That's a second order ordinary differential equation that you can write as two first order ordinary differential equations. So if I define q as being xy, then dq by dt equals lq. Just if I use L equals 0, 1 minus c minus b, I have my first order system. You can work out by hand what the eigenvalue, well, the first eigenvalue is. B is a damping coefficient, so you can see that if B is a real number, then the real part, e to the minus b over 2, is just leading to a damping. I don't want to really dwell on the actual values here because they're very trivial, very simple. But you find sigma 1 the eigenvalue, the right eigenvector, the left eigenvector here. I can do the same for the second eigenvalue. Obviously, it looks very similar. And now, if you want to, if you're feeling energetic, you can check that the eigenvectors are bi-orthogonal. So Q1 dagger, so the left eigenvector, take the Hermitian acted on the right eigenvector. So basically take the inner product of the two eigenvectors, should equal to something that's not 0. So this is what it's equal, so I'd need to normalize each of them by the square root of that to have it equal to 1. But the main point is to check that the eigenvectors are orthogonal. If they are not, that Q1 is orthogonal, Q1 adjoint is orthogonal to Q2, and Q2 adjoint is orthogonal to Q1. Now, this seems trivial, but it's a really good way to check your calculations. If your eigenvectors are not bi-orthogonal, then you know you've done something wrong. So it's really worth doing that check. And then this normalization number here should be the same for Q2 adjoint Q2. So you can do these by hand. It's a little bit boring, but it's a good way to make sure you've done something right. I'll move on. Now let's consider a new feedback mechanism. So if I put in x dot is equal to epsilon x and then the same as before in the other three terms, thinking that physically this is like a sort of negative damping term because x dot is just equal to, I beg your pardon, it's not quite, it will be like a negative damping term, but maybe not quite as easy to spot. Yeah, if you take the derivative of that expression, x double dot will have an epsilon x dot term in it. So put that into the matrix, you'll see that delta L is just epsilon in the top left corner. And now all I need to do to work out how the eigenvalue changes is take the eigenfunction, the eigenvector, pre-multiplied by delta L, which is just epsilon in the top left corner, pre-multiplied by Q1 adjoint, blah, 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 and you get this term here. And you can check that by just going back to this system here, working out the eigenvalues. You can check that the change in eigenvalue is that, and it is. So this is just a really simple example of it working, and very trivial. You can do it for all the other things. This is just the same thing done for feedback between y and x, for between x and y, and between y and y. You'll get different numbers, and again, you can check them by doing finite difference. And then you can also say, let's imagine I change b, which is at the bottom right corner here. So this term here. You can get the change in sigma 1 with the change in b, which is like a change in the base state, changing the system itself, or the change in c, which is like the frequency. So I've whipped through those very quickly, and whenever I do something for the first time, I always try it out on a very simple system. And this was the one I chose, so I just took my notes on it and put them into this presentation. It's a really good way to get started on something, because now we jump into things that are a little bit more difficult to understand in terms of by doing things by hand. So this is a paper that just came out in JFM with Luca Magri, where we applied this analysis to a time-delayed thermoacoustic system with which most of you, or many of you, will be very familiar. So this is, by the way, all the stuff I've just shown you, in slightly different terms, is inside that paper. So if you want to know more details, it's inside that paper. So if I start from a Rika tube, I have the horizontal Rika tube, just like the one that Sujit showed earlier. Airflow over a hot wire inside a duct. The hot wire is at a position xf, and the distance down the duct runs from 0 to 1. I have governing equations here. The first of them is the acoustic momentum equation. It's come from Navier-Stokes. You can tell Navier-Stokes has a du by dt plus u dot grad u. Bah, let's get rid of the u dot grad u. So we ignore convection. We'll ignore the viscous terms. So all we're left with is the dp by dx term. So that's the momentum equation. Here we have the energy equation written in terms of pressure, dp by dt. Now what we have here is, if we just look at the blue bits here, you can see if you eliminate p or u, you've got a wave equation. So those are the acoustics. We add in a damping. Damping is the big elephant in the room for me. I think that the damping is really important. And yet we all, well, certainly I at the moment always say, the damping's simple. I think the damping is the key to a lot of complex behavior. And then we add a heat release term here. This is, oh, Heckel, she's here. This is the one that we have adopted because Sujit adopted it, I think, from Mireille Heckel, originally from Kulik and Matveev, after advice from Wolfgang. So there was something like that. No? Not Wolfgang. Oh, Wolfgang's disowning it. Anyway, I don't want to go into the heat release model, except to say it's the one we used in the paper. It's got a time delay in it, and it's nonlinear. And I think it's a useful way to start for a toy model. And all we're looking to do at the moment is use a simple toy model on this. So we did a Galerkin discretization, which is to say that we said, let's look at the velocity modes and the pressure modes that satisfy the boundary conditions. And I'll express my problem in terms of the amplitudes of these modes. So here's the first one, just a sine wave. P is like a cos wave inside the tube. The second one, sorry, the other way around. This is like a cos, and that's like a sine. And then the next one has half the wavelength, the next one a third of the wavelength, and so on. So we really express u and p in terms of that basis set, and we can keep going up to as high a number of u and I'm not very good at English, modes as possible, thank you. So I just express it like that. When I do that, the problem becomes discretized. And now I get an ordinary differential equation, or a set of ordinary differential equations, in terms of eta, which you can think of as the velocity, the amplitude of the velocity modes, and eta dot, which you can think of as the amplitude of the pressure modes. We linearize. It's worth mentioning this, although don't get too hung up on it. We linearize twice. First of all, for the amplitude, the actual value of UH. So we're looking at small values of UH. U is the velocity at the hot wire position. We also linearize the time delay. So this has a time delay here, and we say that for small time delays, tau, this expression here becomes this expression here. For small time delays, tau, and for small UH. Again, that's described in the paper, but the main point I want to get to here is we've linearized it into a system in which we have a state vector Q that contains the amplitudes of the velocity modes and then the amplitudes of the pressure modes up to n modes. So you can, as Nicolas Noiré did, say let's look at the first mode, but here we add in more and more modes, and we look at, I think, up to, we did the calculations, I think, at 20 modes. I'm looking at you, Luca, but Luca, you went up to 100 modes just to check, I think, and there's not much change after 20 modes. Right, so having done that, this is the model that we borrowed from Sujit's paper in 2008 with Balasubramanian. The extension we've done now is to say, let's imagine some passive control device. So any device at all, but I'll imagine putting it at position XC. And just for illustration, I'll take a device that listens to the velocity at that point. At that point XC. Then multiplies it by some small number, just to stress that it's small differences we're looking at here. Then acts it at that point. That's a Dirac delta function saying that we're going to make this actuate something at that point in space. And it could apply either to the energy equation, we can add it into the energy equation, or into the momentum equation. So this is what I call a passive device, because it's listening to something that happens at XC and forcing something at XC. So for example, a good example in this case going into the momentum equation would be a grid. The drag from a grid is proportional to in a linear analysis, proportional and in the opposite direction to the instantaneous velocity at that point. So if you've got a uniform velocity past a grid and velocity fluctuations, the drag from the grid on the fluid, it would just be the negative of the drag coefficient times these two things here. But if I were doing active control, I could be listening to the pressure at XC and actuating something over here, in which case I just change the delta to X actuator and so on. So you can actually look at the influence of active control as well as passive control, shall we call it, where you just put a passive device into the flow. So I'll look at this one first. So I've taken my acoustic equation, just added on something that listens to the velocity at a position XC and actuates the momentum equation. That gives me a force in the momentum equation. In this case, I'll look at positive epsilon, so it will give me a force in the same direction as the velocity, like the opposite of drag. And this is, so the process is to find the direct eigenfunction, the right eigenfunction, find also the left eigenfunction. And then once I've got those, I combine them. In fact, in this case, I just multiply the left eigenfunction by the right eigenfunction at each point in space, and I get the change in the eigenvalue. So this is a complicated chart. I'll explain this solid line first. The solid line here refers to the left-hand axis. This is the change in the growth rate of our thermoacoustic system, so the eigenvalue in this thermoacoustic system, when I add this passive device, and as a function of the position at which I add it. So this zero line here shows me where 0 is. So if I add that device at 0.5 and a bit, it has no effect. And that's actually because it sits at the velocity node where nothing's happening. If I add that at the downstream end, I find that it has quite a strong effect. In this case, it increases the eigenvalue by a certain amount. But of course, if epsilon were negative, then this line would be negative, exactly flipped around the 0 line, and that would be quite a stabilizing effect. Tim?
So what would happen if you hadn't linearized around small tau? All the theories out the window?
Did you say if you hadn't linearized around?
If you just held on to finite tau.
I think you could do the analysis, but you'd need to be more careful about how you did it. I don't think you could do it with the matrices in this way, but you could do it with forward-backward adjoint looping, which was in my 2010 paper on with involving the time delay.
Okay.
So, I mean, my experience of using time delays in adjoint equations is that it can be done, but if you can possibly avoid it, you should avoid it, because it's quite hard work. It's hard work actually because you don't know what happens before time zero. So before time zero, you've got this period of time where you don't know what happens, and then at time zero, you start using a value minus some time.
Period rather than initial condition, right?
So,
You have an initial period
yeah,
rather than
yeah.
initial.
So you have as many new degrees of freedom as there are time steps in that initial period. So that's why recently we've been trying to drop the time delay and simulate the flame.
But I would assume that with finite damping, that initial period, hopefully would go, the solution would become independent of the initial period if you're losing memory.
If you lose, yes, the more you lose memory, of course, the
So
better it
finite
gets.
damping, your zeta term.
Yeah. So, but you'll still need some knowledge, won't you, of the initial period?
But I'm wondering, I guess what I'm asking is the solution independent of the initial period?
I don't think so. I think it would depend on the initial period. Yeah, so, I mean, yeah. I think, to sort of summarize it, I think you can linearize for a small time delay in this case, or rather, when one linearizes and just has a matrix, well, dq by dt equals L times q, then you can use all the matrix algebra, and it's really easy. If you include the time delay, you can still do it. The way I've done it is with adjoint looping, so you do a time march forward, a time march back. You can definitely do it. There may be an easier way, but I haven't found it. In fact, I think, Wolfgang, you've tried a way with a large matrix that sort of shunts all the time steps, so you can do it with a matrix method. Yeah.
There's approximations, like there's Padilla approximation and there's other
Yeah.
approximations for that time, so you can get arbitrarily close to that time. So
Mm.
Yeah, but all those have a finite domain of attraction. It seems to me that what makes the combustion instability problem really interesting is because tau is on the order of a period. Or I'm not sure that those fall within that domain of attraction.
as soon as you get as close as possible, I mean, it's an arbitrary decision how much degrees of freedom you want to introduce, and then you get like to that time. So.
No, I understand.
Wolfgang, you want to say?
I was going to say, as you're looking at eigenfunctions and eigenmodes and eigenvalues here, I don't see the problem with the early information before t equal to 0, because for the eigenmode, you know what the mode has done also for negative times, right?
Yeah. So maybe there's no problem.
There is no.
Also for relative time delay is indeed very short. Maybe
Yeah.
for flames it's
Yeah. I think, to wrap this up, I think, it's a great discussion for a cocktail later. To wrap this up, I initially did the analysis all for time delays with the forward, backward, adjoint looping. It can be done, it's a headache. What we've tried to do now is get rid of the time delay and actually simulate the flame. This with a short time delay I think is okay for a very thin wire, but obviously for a flame, where the time delay is of the order of a period, if not more, I wouldn't use this method. Yeah. Well, I wouldn't say that this would go straight over to a flame. I think you'd have to simulate the flame. Or use a forward, backward, adjoint looping. That would work. Anyway, where was I? So we're looking at the effect of the growth rate of this make-believe feedback mechanism. So we've taken a feedback mechanism that listens to the velocity and gives you a force in the direction of the velocity locally at position xc. We discover that that has very little influence in the middle because there's a velocity node in the middle. It has most influence at the downstream end and the upstream end of the tube. It's not quite symmetric because there is heat release in the problem. If there was no heat release in the problem, then this would be a nice symmetric cos squared shaped curve. This dashed line here is the effect on the frequency. The 0 for this is the dashed line here. This is the scale on the right-hand side. And you can see that the effect of this feedback mechanism on the frequency is very small. So this feedback mechanism, which could be, say, a grid put in the flow, and that would give you a drag force in the opposite direction of the velocity, and therefore it would be most stabilizing at the downstream end and quite stabilizing at the upstream end, would have very little influence in the middle. But any sort of feedback mechanism like this has very little effect on the frequency. But I highlight we got this from 2 calculations, each of which must have taken a millisecond. So it's a really quick way to work out all of this information. And obviously this system is small, but it scales up to big systems as well. And we checked all this with finite difference as well, just to be sure, which takes a bit longer, but it's worth doing. I'm going to present all four of these, but I'm going to focus next on the bottom right one. This is where we said we're going to listen to the pressure and then force the energy equation. So this again, for the moment, this is a make-believe feedback mechanism. We're listening to the pressure, forcing the energy equation, this one here. And we can see that this has most influence around the center of the tube, which is where the pressure fluctuations are largest, and the sensitivity to the energy equation is also largest. And it has no influence at both ends of the tube. The black line corresponds to this axis here, which is large values. The dashed line corresponds to the right axis, which has small values. So again, we see that this type of feedback mechanism has very little influence on the frequency, but a very large influence on the growth rate. It's worth thinking about what this might represent physically. In solid rocket engines, if the pressure goes up, the rate of combustion goes up. So this is an example of, a solid rocket would contain fuel that would have these characteristics, that the combustion rate, the heat release rate would increase as the pressure increases. And in fact, there's a nice paper, is it by Chu in about 1962, where they look at the simulation of a solid rocket engine, and they find that well, first of all, it oscillates most in the middle of the tube, as you'd expect, but also that it's extremely unstable. I'm not so worried about what the physical mechanisms are just at the moment. I just want to get the building blocks. The next one is to say, what happens if I listen to the velocity and force the energy equation? So this is a bit like having a hot wire, another hot wire in the flow with 0 time delay. So it listens to the velocity and then increases the heat transfer to the flow as the velocity over the wire increases. Now this is interesting. The black line corresponds to the left-hand chart. This is the effect on the growth rate, and you can see it has a very small effect on the growth rate. But the dashed line for the right-hand axis has large values. It shows that it has a big effect on the frequency. So this mechanism here, which gives you heat as a function of the velocity, heat input, extra heat input as a function of the velocity, greatly influences the frequency, but doesn't influence the growth rate very much. And again, that's because the heat release is in phase with the velocity. Everyone quotes Rayleigh's 1878 paper about how if you compress something, add heat, and then uncompress it and take away heat, which is the integral of P times Q over a cycle, you put energy into a system. Just underneath, he says, and if the heat be in phase, he's writing in 1878, if the heat be in phase with the velocity, then you change the frequency. But it tends not to be quoted quite as much. So that's really an example of that happening. So this sort of feedback mechanism, which is rather like another hot wire with a 0 time delay, changes the frequency but not the amplitude of the oscillations. And then the fourth one up here, I won't talk about. It's just listening to the pressure and forcing the momentum equation. Up to you to think of an actuator that does that. Anyway, having got these building blocks, which again, each of which took milliseconds to calculate, you can then ask more interesting questions like, let's imagine I put another hot wire into the tube somewhere. What effect will that have on the growth rate and on the frequency? So this says here the real part of d sigma by d beta c. Beta c is the hot wire temperature. So this is saying how the eigenvalue, the real part of the eigenvalue, so how the growth rate changes with the hot wire temperature. And just follow the black line here with circles on it. It's very similar to what we had at the bottom left down here, but because I've included a time delay now, it's not exactly the same. We get the drift of the growth rate. As expected, it's small. And we get the drift of the frequency. As expected, it's much bigger when we add this control hot wire in. And we see that if we add the control hot wire in around the original hot wire in the first quarter of the tube, first half of the tube, it's most destabilizing, as you'd expect. If we add it at the velocity node, it has no effect. If we add it in the second half of the tube, it's most stabilizing. We knew all this already, but it's just a good check. And then we can compare it with the Rayleigh index, so we can actually work out the increase in energy over a cycle depending on where the new wire is. And what's important to note is that the 0 values are the same in both cases. The top one is actually more accurate than the bottom one, because the Rayleigh index assumes that you're in a cycle, whereas in actual fact you're growing over a cycle. So the only really important thing is that they cross at the same point on the axis. The fact that they look the same is expected, but they shouldn't look exactly the same. So basically we just use the technique to show something we already knew, but really is a demonstration of the technique in thermoacoustics. Now, having said that, we started from a nonlinear case with a time delay. We work out a control strategy based on, in this case, adding a hot wire. And we can actually do the nonlinear simulations just to check that everything is as we expect it to be. So we start off with an unstable system, linearly unstable with exponential growth. It's nonlinear, so if this carried on, it would reach a limit cycle. At this point, 1000, we turn on the control hot wire, and we see the frequency change from this to, we get a frequency shift, and we also see the growth rate change. And we could work out the growth rate, and it was exactly as expected from the linear analysis. We helped ourselves by making the amplitude very, very small, and a very small time delay. So I'm not pretending this is some profound result. It was really just a check of the direct adjoint looping, the sensitivity analysis that we'd done before. So that, in a nutshell, is what's in that paper. We've since extended that to the Burke-Schumann flame, which was the other paper that Sujit and Balasubramanian published in 2008, where we have a diffusion flame inside a tube, and Luca will present that tomorrow. I think that this technique has enormous potential in all sorts of areas in which a linear analysis is used, but particularly in thermoacoustics, because you can say, I've got some acoustic system, thermoacoustic system, and in 2 calculations I can work out which bits of that system have most influence on the eigenvalue if I were to change them, and indeed how to change them. We can also say what happens when we change the hot wire temperature and the time delay. I'll actually skip that because I want to, I've been going now for about 45 minutes. It'd be time for a break, wouldn't it, Bruno?
Yeah.
Bruno.
I give 2 simple observations. You said if these 2 calculations, is there some optimum and...
Is there an optimum perturbation? Absolutely, yeah. The Frobenius norm of the matrix. Luca will correct me if I'm wrong. So you take the adjoint eigenvector and the direct eigenvector, and now instead of doing that times that to give you a number, you do it the other way around. That times that to give you a matrix. I think you take the Frobenius norm of that matrix, and it gives you the biggest possible influence you can have, and will tell you the mechanism that would give you that. So you could work out the mechanism that would give you the biggest change to the eigenvalue, and where to put it, and so on. In fact, I'll more or less be showing that later on. I just want to give some examples of where we've used this before. This is perhaps slightly inspired by Olivia Pacherite's talk yesterday. This is the swirling vortex breakdown bubble. So if this is a gas turbine combustor and this is a vortex breakdown bubble, the flow comes around that, and behind it you get this spiraling instability. Wolfgang asked the question yesterday, is it an axisymmetric instability or a spiraling instability? Which comes first, I think. And as you increase the swirl in a pipe, it's very sensitive to the shape of the pipe. You start off with the flow just being a swirling Poisson flow type thing. And then you find you get an axisymmetric bubble forming, rather like a hydraulic jump forms. It just forms, but it's a stationary, it doesn't change in time, it just sits there stationary. And then if you increase the swirl slightly, then you get this spiraling mode that appears on top of it. So actually the 2 things happen at a very similar time, which I think is why people weren't sure whether you got a spiraling mode or a axisymmetric mode first. It depends a lot on the boundary conditions. And actually,
it appears on top, so the bubble type stays while the spiral
yeah.
develops in addition.
So you find that the flow is a sort of Poisson flow with a swirl. As you increase the swirl, you get a recirculation bubble forming. As soon as it forms, well, it's very nearly unstable when it forms. As you increase the swirl or the Reynolds number further, then the spiraling mode becomes unstable on top of that, or that axisymmetric flow becomes unstable to the spiraling mode. And John Healy wrote a very nice paper on it, John Healy from Kiel, on when you get one, when you get the other, in which order you get them. And it's extremely dependent on the boundary conditions, as Oliver said yesterday, actually. So this is the flow we'll look at. Now, what I'll do, and this is in a paper in JFM that's just come out, these are the streamlines of the flow. So the colours represent the amount of swirl. The black lines represent the streamline in the axial and radial directions. So the flow's coming in here, going around this recirculation bubble, and you get a sort of what's known as Lamb's bulges afterwards. In this region here, we have a recirculation zone And you can see it's not swirling very much, but that's not terribly important. And we use this as a sort of a prototype for the vortex breakdown bubble in a gas turbine combustor. And so we've applied these techniques of receptivity and sensitivity analysis with the left and right eigenfunctions to this. So let me talk you through what each of these means. This is the base flow. This is the center line, by the way, is along the bottom axis here. That's the radius up there. The second one down is the shape of the most unstable mode. That is the direct eigenfunction, the right eigenfunction. So if you take this flow, which is unstable, and you let it grow in time, the shape that grows the fastest is this one, and it's a spiraling mode, the one that Oliver showed yesterday. So you've got this base flow here. On top of it, you get this spiraling mode growing.
Smith, that's the wake. The spiral is in the wake of the breakdown bubble.
The spiral, yes, the spiral is in the wake of the breakdown bubble. So you'd be tempted to think that it's caused by the wake of the breakdown bubble.
Yep.
Now, this is the direct global mode, also known as the right eigenfunction. This here is the adjoint eigenmode, also known as the left eigenfunction. I'm trying to think what the contours are of here. I can't remember. It doesn't matter a great deal. The most important thing is where it sits. The adjoint eigenfunction sits in this upstream region here. Just taking a step back, we've talked about non-normality a bit. We've talked more about non-linearity. When we have convective flows like this, waves tend to get washed downstream. And the adjoint, the left eigenvector, does the reverse. It tends to get washed upstream. And the reason that these don't exist in the same place is because of the non-normality in the system. If the system were normal, these two things would be exactly the same. I just mentioned that to try and link into the non-normal and non-linear. In hydrodynamics, one sees an enormous influence of non-normality arising through the convective terms in the governing equations. Anyway, this is the adjoint eigenmode. It's also, another way of looking at it is the receptivity to external forcing. So if I put in some forcing signal into the flow, this is where that forcing signal will have the biggest effect on the growth rate or the frequency of this spiraling mode. So I didn't talk about that before. It's another way you can use the adjoints. I won't say any more about it now. This is perhaps the most interesting thing. This is actually the Frobenius norm of the matrix. When you take the left eigenfunction and the right eigenfunction, multiply them together to create a matrix and take the Frobenius norm, this gives you the position of the flow that is most sensitive to feedback. And this is the bit of the flow that is causing the instability. So think of that as the wavemaker region. So this bit of the flow here, which is at the front of the recirculation bubble, is oscillating, or wants to oscillate. And actually the rest of the flow is just responding to that oscillation. So although it looks from this direct global mode as if it's behind the bubble that is causing the oscillation, it's actually in this case the front of the bubble that's causing the oscillation. But because the flow is being convected that way, it starts here with this low amplitude and then grows as it goes downstream. I'll say more about that in a few slides' time. But that's the sort of information you can get from this analysis. And again, it's just two calculations. So it's very quick. And I show here the sensitivity to base flow modification. Basically, this is showing that if I want to change the frequency or the growth rate of this oscillation, the bits of the flow I need to change sit at the front of the bubble, not behind it. And again, that could come as a surprise. Wolfgang.
Question on receptivity and sensitivity. I mean, the way you presented the method, I would have thought, okay, if I want to know how the eigenmodes change, if I change the flow at position 2 and 0.3, right?
Yeah.
Right there. I have to put in a delta L that represents that change, then do my two calculations, and then I have that information at that one point.
Yeah.
If I want to know how the sensitivity is at 0.1 and 0.3,
Yeah.
I have to do this over and over again. So in order to have a contour plot like that,
Yeah.
I would do lots and lots of calculations now.
Yeah.
But still you say there are only two, so there is more to it than...
Ah, yes, because you actually do it the other way around. You find the direct global mode, the adjoint global mode, and you never have to calculate those again. Now, you could, if you wanted to, take your L matrix, find the delta L that represents some feedback or change in the base state at that point, and then do, in fact, that's probably the best way to do it. Adjoint that delta L times the direct. But you can change the delta L without ever changing the left and right eigenvectors. So that's the beauty of how it works.
You do the hard work once and then you
Yeah, exactly.
exploit it all the time.
You do the hard work once and then you just use it lots of different ways. Yeah.
Is this picture that you're seeing, the contour plot, is it like those are points that are points of highest sensitivity, or is this like, this is the eigenvector, so we see the vector, you need to move the whole thing and like...
So this is, yes, it's the overlap of the left and right eigenvectors, which has a value at each point in space. Now, to get the biggest effect on the eigenvalue, well, I mean, you could change each of those in, or you could, basically what it's saying is if I put some feedback device in at that point, then I get the most effect. I could put the same device in at that point and I'll get slightly less effect, and so on. Maybe it wouldn't be quite the same device, but it's a sort of way of showing which part of the flow is oscillating and which part, and then which part is responding. I don't feel I've quite answered your question. No.
Yeah, it's like, well, when I want to create an actor, I would need to project the actor onto this vector that we're seeing here.
Yeah.
And then I would get the effect on...
Yeah, I mean, what you do, as Wolfgang was saying, you've got the right eigenvector, you've got the left eigenvector. You can express your actuator in terms of a matrix, or dq by dt equals delta L times q, and then you just do that multiplication once and you'll get the effect of that actuator. Yeah. And what we've done here is just say, I'm going to imagine the best possible actuator. Where does that have the most effect? And that's what that picture is there. Right, I'll move on. Now, what we can also do is say, let's imagine dissecting this feedback. Let's look at the feedback between the axial velocity and the axial momentum equation. This is the recirculation bubble here. I'm sort of just zooming in on the first little bit of the flow. So here's my recirculation bubble. And I find that if I have some actuator notionally made that listens to the axial velocity and then increases the axial momentum, it has most effect in this region here. I can do the same for all the other components. And this is really worth bearing in mind. And this is in the paper that we've just published, this one here. You see this has a high amplitude here, here on the front leading edge of the bubble. Whereas here, feedback between the radial and the azimuthal velocity and the radial and radial has most influence at the front of the bubble. So we can see two regions. And by looking at the sort of signature of the Kelvin-Helmholtz instability, a Kelvin-Helmholtz instability has strong feedback in these 5 components here, whereas a feedback mechanism involving angular momentum conservation has strong feedback between these 4. And so what we find is that there are 2 instability mechanisms inside this flow. One of them is the Kelvin-Helmholtz, which is due to the shear in this region here. And the other one of them is to do with conservation of angular momentum. So it could be a centrifugal instability, or it could be one that involves the Coriolis force. And it has most impact at the front of the bubble. And so by looking at the components of the structural sensitivity, you can start to dissect the different instability mechanisms in the flow. Tim's forehead is furrowed, as indeed was mine when thinking this through. And I think that this has legs in the sense there's a lot more analysis to do in this direction. I think we can say with some certainty, because we looked at flows in which we just had a Kelvin-Helmholtz mechanism, and you see big values on these 5. We looked at flows which just had a centrifugal or a Coriolis mechanism, we see big values in these 4. And I think in this case we get a Kelvin-Helmholtz mechanism around the front edge of the bubble where there's strong shear, and then a Coriolis mechanism around the front of the bubble here, where there's, well, essentially when actually small perturbations to the azimuthal or radial velocity get strongly amplified by the fact that the flow is concertinaing. Let's not dwell on it too much just for now, but you can start to dissect what is important in the flow. And it's worth mentioning that the local analysis will only pick up the Kelvin-Helmholtz modes. It won't pick up these ones here. This is This is another application. What we're going to look at now is the instability of a helium jet. The reason for doing this is that I've done everything so far for incompressible uniform density flows. But the question is, can we do this for flows in which the density varies? And particularly for combusting flows, because that's a step towards doing a thermoacoustic problem. Everything so just up to here has been hydrodynamic. This is the helium jet, a low-density jet coming into air, and you can see that it beats at its own frequency. And what I'm going to do now is say, how can I change that frequency by changing certain aspects of this injection? So I'm going to turn it on its side. This is work done by Ubaid Quadri and Gary Chandler. So here I've got the streamlines. The streamlines in the middle are the helium jet, and then the streamlines here are the air on the outside that is being entrained by the helium jet. So it's on its side. I've found a steady base flow, so it's a steady solution to the Navier-Stokes equations, but it's unstable. So if I was to start off from that, we'd see this bulging mode appearing on top of it. So it's a steady but unstable solution to the Navier-Stokes equation. Here I've shown the absolute growth rate, the local absolute growth rate, much as Oliver was showing yesterday, but I won't talk about that anymore. This is the direct global mode, which is the right eigenvector. This is the adjoint global mode, the left eigenvector. You can see they're not the same because the system is non-normal. And if you don't remember anything else, that's a really useful thing to remember. And we'll overlap these in lots of different ways to get all these sorts of sensitivities. Now, maybe I'll just pick one of these. And maybe I'll pick the one that's closest to me here. This is saying, let's imagine I can have some device that inputs a steady heat into this flow. And the jet comes in with a radius of 0.5. So this is the center line here. The jet comes in at 0.5. This is showing me that if I heat the flow just outside the jet, I stabilize, I reduce the growth rate of the oscillation, which is what you expect actually, because this is driven by shear, but also by a density difference between the two flows. So if I heat up the air on the outside, I can stabilize the flow. Interestingly, you can also change the frequency quite a lot, which I wasn't expecting. But by putting this extra heat input outside, you can change the frequency. Now, we're actually going to do some experiments on this. Actually, I'll come to that in a moment, because I'll describe the device that we'll use to do the experiments. But you can see the change in the growth rate due to some steady input of heat, or if you like, an axial force or a radial force. But I think that the heat is the easiest one to explain. And again, two calculations, very quick to get all of this information. Now, this is the sort of the building blocks. In reality, you'd have to put a device into the flow. The device that you could look at would be a ring. You can imagine a ring that goes into the flow that doesn't have any heat transfer. We call that an adiabatic ring. Maybe it's made of plastic. And the most sensitive place to put that is at this point here. This is its effect on the growth rate. It's strongly stabilizing in this region here. And this is its effect on the frequency. Again, it has quite a big effect on the frequency. The black lines, by the way, are the contours of the absolute value of these two numbers. So at the center of it, which is about there, that's where you have the most influence overall, and it's a stabilizing influence. So if you have an adiabatic ring, made of plastic, whatever, the best place to put it to stabilize this oscillation is at this point here. And we'll be doing experiments on that shortly, or Larry Lee will be. I think we'll look at the stabilization, but I think the easiest thing to look at will be the change in frequency of the oscillation. Much easier to measure experimentally. Now, if you imagine a hot ring, so a wire that you heat up, where's the best place to put that? Well, not quite the same position. If you put it a bit further out, then you heat up the flow outside the jet, so you reduce the density difference between the outer flow and the inner flow, and therefore you make the flow more stable. Once again, two calculations to get all of these, very, very quick. And yet it gives you a lot of information about how to change the growth rate of and the frequency of a given oscillation. And I think it has great potential both in hydrodynamics and in thermoacoustics. We're nearly there. What I want to talk about next, flames. Oh, by the way, just note the values here, 10 to the power 4. Don't worry too much about the absolute value. The sensitivity of these things is of order 10 to the 4. 10 to the 4 things, and compare that with what we're going to see in a moment. This is a jet diffusion flame. So again, we have a jet coming in here. It's set to be a hydrogen jet diffusion flame, so low density coming in, air on the outside. We get a triple flame structure here, and then a diffusion flame between the reactants inside and the oxidizer on the outside, and the products developing along there. And what we're seeing here, streamlines of the flow, there's no swell, and contours of the reaction rate in colour. So we can do the same analysis for this lifted jet diffusion flame. This is very interesting because actually we find two wavemaker regions. Again, this is so basically we find one eigenvalue. We find its eigenvector and its adjoint eigenvector, so its left and right eigenvectors, overlap them, and we get the top picture here at a high frequency. But there's also another eigenvalue. So we take its eigenvector and its right eigenvector and its left eigenvector, overlap them, and we get this shape here, and this is at a lower frequency. So this flame it can oscillate in two ways. It has two unstable eigenvalues. The first of them is at high frequency and is driven by this part of the flow. If you like, it's the non-reacting part of the flow, and it's the same mechanism that gives rise to the oscillation of the low-density jet. And then you get the flame front here, you get gas expansion, you get now a change in the velocity and the density profiles, and that generates another oscillation at a much lower frequency, which is based in this part of the flow. So these are things you can get by overlapping the direct and adjoint eigenfunctions that, again, I don't think you get just from looking at the direct eigenfunction itself, because you can tell which bit of the flow is causing which oscillation. Now, I'll show one more picture from this case, but it's a very interesting case. We've included in this analysis, which is a global analysis, the effect of the fluctuations in the reaction term as well. And that becomes very important when one looks at the sensitivity. This is to the first mode, this is to the second. This is saying, let's put some steady heat input. What's really interesting, I find, is the size of these. That once you've got a reaction in the flow, the system becomes extremely sensitive to any changes. And I'm still getting to grips with what this means. We haven't published this yet. We're still writing the paper. But what it seems is that because we've included the reaction terms in the linear stability analysis, these are exponential terms, as you might expect, a small change in, say, the temperature has a big change on the heat release and therefore on the density fluctuations, and these are having big effects on the hydrodynamic instability. And you might call it hypersensitivity. It's certainly extremely sensitive to some changes. And I just flag it up because I think it could well be important in thermoacoustics. We know from experiments, Nader Karimi, who's a postdoc in Cambridge, was sort of saying the other day he did an experiment, went away, came back to do exactly the same experiment, completely different thermoacoustic behavior. And it turned out there was a very small leak in where the join between two, he had a quartz tube and a steel tube, and there was a small leak between the two. So it seems that in thermoacoustics, the system is extremely sensitive to some things. And it could be that with the overlap in the direct and adjoint eigenfunctions, we'll start to work out what those things are. That's just pure speculation. We'll have to see. We've finished. This is my final slide. And normally at this stage, I'd have some pretty pictures with some text saying summary, etc., etc., etc. But I think I can summarize it like this. If you've understood this, you've understood the whole thing. In order to work out how an eigenvalue changes, given some operator L, we find the direct eigenvector of the operator L, we find the adjoint eigenvector of the operator L, and then we do this calculation here so we take the adjoint eigenvector on delta L, the change we want to look at, which can be any change we like, and operate that on the direct eigenvector normalized, and we get the shift in the frequency. So the big calculations that's the biggest calculation to find out the eigenvalues and the eigenvectors, or maybe just the few that you want to do first of all. The second one here is another big calculation, not quite as big as the first because you know the eigenvalue that you're looking for. Once you've got the left eigenvector and the right eigenvector, you've done the big calculations, and the rest is just how you put them together to work out the change in the eigenvalue with respect to the change in anything at all in your operator. It could be an active feedback mechanism, a passive feedback mechanism, a change in the base flow, whatever you like. So if you've understood that, then you've understood the talk. And the rest was just pretty pictures. Thank you. That's all.